So we're talking about consensus authoring today. Like I said, this is the first of 2 consensus lessons. The next one's going to be about finality. This one's about authoring. So, all right, let's start by framing this. Consensus is a decision-making process. The goal is to achieve acceptance of a decision by all participants. So it doesn't mean that every participant is going to get their way. Anytime there's a difference of opinion, at least someone is not going to get their way. But ideally, the consensus mechanism will have everyone believing that the decision that was made is legitimate. So that's what we're striving to do. And then to narrow it down to get a little bit more focused on blockchains that we're actually talking about, blockchain consensus is a decentralized consensus system to reach agreement over a shared history of a state machine. So we already saw in the previous lesson how the blockchain data structure can track histories of a state machine, and consensus is going to help us narrow down which of those histories is real. So let's talk about block space just a little bit more. This is a block space creation machine. It takes as input users' state transitions, aka transactions, aka extrinsics, and it outputs this blockchain data structure. And the product here in the blockchain is the space inside the block body. Basically, we have some limited amount of resources in the block body, and we'll talk later in the course about the ways in which the space can be limited. It's not always just about like literal bytes and having a byte maximum, although sometimes it's that. And so basically the idea is if there's a lot of transitions trying to get their way into this machine or like waiting in the queue, the transaction pool over here, only so many of them can fit in here. And what the consensus does is it offers this block space as a product that users want to consume. So the consensus system itself basically has a lot to do with the quality of the block space. And so what I mean by that is if this is some like kind of janky decentralized network where it's not really that decentralized, maybe there's like 3 nodes and 2 of them are mine and one of them is like, you know, my best friend's, that's going to be pretty low quality block space because it's pretty centralized. But if, on the other hand, the network is like very decentralized and very resilient to attacks at all layers, and it reaches fast finality and has high throughput and things like that, that's typically going to be considered high quality block space. And so we'll start to see like, you know, how we can build these different consensus systems. But at the end of the day, the whole point of the consensus system is to track the history of the state machine and offer up the ability to interact with the state machine as a product called block space. So quick review of forks. Here we see like a blockchain network, or blockchain data structure, I should say, that has a bunch of forks. And we can rule some of them out. So for whatever, we've ruled out this one and we've ruled out this one, and that narrows it down to basically like 3 candidates for what are the best chain. This candidate, and this candidate. So just because this one had an invalid descendant doesn't mean it's ruled out as a candidate itself. So you can think of this at like a social level. You can think of it as like court cases, arguments, wars, whatever. Ideally, we can resolve these things peacefully, and what we're trying to resolve is which history is real? What's our story? What is the history of the state machine? Or you can think of it a way that I like to think of it, which is at a more low, like physicsy level. So disclosure, I was a physics major, and so I like physics. And so if you think about like every time an electron is bouncing around, it encounters some potential barrier, it either like bounces off, reflects off of that barrier, or it like tunnels through into the next like potential well. And so when consensus is high quality, the result is as objective as the outcome of a physical process. Like if you think about looking for an electron, did it tunnel or did it not? Once you make that measurement, you know physics decided. And high quality consensus offers block space that's similar to that. I don't know if it will ever be as high quality as literal true physics. But if you're familiar with like the many worlds interpretation of quantum mechanics, you can think of these as like the many worlds. So maybe like in this history, the electron tunneled, and in this one, it didn't tunnel. It's still in the original well. So if you like physics, that's an analogy you can keep in mind. If you don't like physics, just think about it as deciding who wins a court case. That's totally fine too. But you should like physics, I would say. So I'm going to break consensus down into 5 categories. There's a million ways to slice this thing. This is the one that I'm going to do this time. And if it goes well, I'll keep it. And if not, I'll revise it for next time. But I think everybody would agree that these are like relevant points. So the first one is state machine validity. The next is these like arbitrary and political validity rules. Those two are like pretty simple. I'm going to talk about them really quick in the next few minutes. Then there's authorship throttling and fork choice heuristics. That's what I'm going to talk about for like the bulk of this lesson. And then there's finality, and that's the lesson that's going to come up first thing tomorrow. So these first three right here, these are all about ruling out possibilities. These are all about saying, like, I saw a bunch of forks in the chain, I'm throwing some of them away to reduce the scope of the problem set, to reduce the number of possibilities that we need to decide between. And then these last two, these are about ruling in possibilities. These are about saying, like, once we've reduced the problem space a little bit, these two things are going to help us actually finally make a decision and say, this is the real chain. Okay, right, so quick review of state machines. I think you guys have seen this one before. I know you have, I showed it earlier. So at the state machine level, some transitions are invalid. So does anybody see any invalid transitions? Yeah, I heard someone say the second one. The problem is if the switch is off and you toggle it, it doesn't stay off. So if your blockchain history has something like this in it, we can throw out whatever block has this transaction followed by this state, or as we know, actually the block will only have the state root, but like similar concept. And the reason is because that doesn't even follow the state machine rules. So to just go back real quick to my 5 like concepts. Oh, there's the stragglers. Just kidding. Welcome back. I'm glad you're here. So that's my first point here about state machine validity. If the transition doesn't even respect the state machine rules, we throw it out right away. Okay, so the next one is these arbitrary or political validity rules, and it's really similar to the state machine validity rules. You can almost think of it as like slight disagreements about what the rules of the state machine are. So let me just give you some examples here. Some people might have opinions about the size in bytes of a block that's allowed to be included in our blockchain. This seems a little bit frivolous, but this is actually like one of the most famous contentious questions in Bitcoin's history, the great Bitcoin scaling debate of 2017 when they forked into Bitcoin and Bitcoin Cash. So basically, some people think that we should allow big blocks, and other people think that we should only allow blocks up to 1 megabyte in size. And what that does is it causes some people to rule out blocks that are bigger than 1 megabyte. So people who have that opinion, maybe this is like a block that's 2 megabytes, and so the small blockers would just rule that out because of the like political view. So some other examples of like political views, like maybe blocks that have like hack transactions, many people will consider them invalid. Now, it should be pretty clear that the definition of hack is like pretty subjective, you know? So one man's hack is another man's like valid state transition, right? Like you wrote this smart contract code that does X, I made it do X, now you're telling me that doesn't count. But on the other hand, like sometimes when there's a big hack, people are like, wow, we are not, like everybody lost their money and got wrecked. There's one person that exploited it. We're gonna like fork around this. We're not gonna allow that transition to be considered valid. Another one is like some people don't want empty blocks in the network, blocks with no transitions in them because they say it's just like a waste of resources, everybody has to sync them. And then just to throw out like a ridiculous one, this isn't one you'd likely see in reality, but it's a perfectly good example of what could be political or arbitrary validity rule. Like maybe somebody wants to accept only blocks whose state roots are even. Like why? I don't know. That's like a weird thing, but it's exactly the kind of thing that somebody could decide on. Okay, so that's my first 2 categories. There's the state machine validity ones, and then there's these like arbitrary political rules. And both of these things allow you to rule out various block possibilities. Question or comment?
So how are these political views enacted? I write a custom node and just say my node is going to operate on this network, but
exactly.
not do that.
Yep, that's exactly right. And it doesn't have to be that every single person writes their own custom node. It could be that you write the custom node, and then I'm like, yep, I agree with that political viewpoint. I'm going to run your node instead. Okay. And then it may be that at some point your node becomes known as Ethereum Classic or Bitcoin Cash or something like that. Okay, so the third of the 5 points is authorship throttling. So real-world blockchains impose rules or restrictions about who can author blocks and when. So let me just start with this question. Like, these blockchains are supposed to be permissionless. I blabbered on and on for several minutes this morning about how permissionless is like one of the desirable properties that we're trying to achieve. And so in some sense, it seems like we should just let anyone author a block anytime they want. That sounds permissionless. So why? Why would I want to throttle the blocks?
If you have too many options to choose from, then it's going to be hard to reach consensus. It's going to take too long.
Yeah, exactly. Look at this block tree right here. Look how many forks there are. Everywhere. Forks here, forks everywhere. It's forking crazy. We do want it to be permissionless, and we're going to try to find ways to keep it as permissionless as possible. But if everybody's authoring blocks every other moment, they're going to be coming across the network like faster than I can download them and faster than we can run our consensus rules to decide between them. So the reality is we just have to like slow it down to some reasonable rate. And you can think about the rate in terms of like blocks per minute or megabytes per minute or like execution time per minute or however you want. It's okay that it's a little bit squishy right now. But the point is it can't just be raining blocks left and right. We have to keep it at some reasonable rate so that the consensus engines can keep up with it. Okay, so just to recap, we have the state machine validity, the political validity, and now we have authorship throttling. And basically what that means is we're going to have some protocol in place to choose which person or entity or people or entities are allowed to author the next block. And that's just going to help us when we get to the next phase of consensus, which is finality, because it's going to keep the problem space like small enough that we actually can decide between all of the options. Okay, so we need, like I said, we just need to like elect a small or ideally single entity who's allowed to author like next. So I should also say, I didn't say this yet, distributed consensus is actually a pre-blockchain concept. Even before blockchain was around, it was often the case that people would run like servers all over the world working on some problem set, and we wanted to reach consensus over like the shared database. It looked a little bit different. They didn't really have permissionless as a value at the time, and they didn't really have censorship resistance as a value at the time, but it was the case that you would see these like distributed systems that were trying to reach consensus over something. So just to give you like a very quick example, if you think about instruments on an airplane, whether it's a human pilot flying or an autopilot flying, there's like certain things that the pilot needs to know at all times. One of the most critical ones is airspeed. And so you don't want to just have a single airspeed sensor because the moment it gets clogged with a bug or iced over or falls off or just gets old and stops working, then the pilot's like kind of flying blind. And so you'll have multiple of these sensors and we just need to reach consensus about which one's real. Now that's like a much less malicious environment because you're not worried about the airspeed sensors like lying to each other or like trying to deceive each other or stall consensus. It's just a matter of like if one of them breaks. But all this is to say that blockchain uses this computer science idea of distributed consensus, but it wasn't new, although there were some innovations. So all that to introduce this term leader election, which predates blockchain, and leader election is the process of deciding who gets to author the next block. And I guess I'll just right now introduce this concept of liveness. It's the ability of a system to keep authoring new blocks. So it's a desirable property that consensus systems want to have. Consensus systems that have better liveness properties or like are more live, are less likely to stall, those offer higher quality block space. And so applications that are thinking about consuming the block space of this chain or that chain, one of the things that they'll look for is liveness. Just like in the same way that when you're looking to like buy a car, you might consider like how many seats does it have, how fast does it go, what's its gas mileage. This is just like one of many ingredients into like quality block space. In chains without good liveness guarantees, they become stalled sometimes. So has anyone heard of a blockchain that has downtime sometimes or a lot of times? So let's look at some of these block authoring mechanisms. I should say block authoring. So I'm going to call them block authoring mechanisms. That's what everybody calls them. Keep in the back of your head, it doesn't like somehow teach the node to author a block, like any node could author a block. What they actually do is they throttle the block authoring, okay? So they're really, like a better term might be like leader election mechanisms. Did you want to say something? Okay, yeah, but anyway, just keep that in the back of your head, and from now on I'm going to say like authoring mechanisms or authoring engines just like everybody else does. It's just like a slightly less than ideal term. So proof of work is Satoshi's big invention. So like I said, this concept of leader election wasn't new with Bitcoin or blockchain, and actually the concept of proof of work itself wasn't new either, but using proof of work as a leader election mechanism and a distributed consensus mechanism, that was new. So does anybody know what proof of work was originally for? Has anyone heard of it? Okay, go ahead. Oh yeah, Nuke, whoever you guys give the mic to. Okay, it's a race.
Sorry, no, it's okay. It was for mail spamming avoidance, right?
Yeah, exactly. So how's it work? Tell me a little bit more.
I don't exactly remember. I know that was the reason that it was invented, so it's time to shine.
Okay, all right, that's cool. So yes, it was for email spam resistance. That's exactly right. So consider that I have some genius scheme and I want to market it out to all of you guys so that you can all invest and buy my magical product or whatever. And I just start sending out email everywhere. Everybody hates spam, right? So the idea is you attach some proof of work to the email protocol. So in order for your email server to accept my email, I have to show it that I did some computational work. In practice, it's solving a pre-image search. So you guys learned about hashes, I know. And basically the idea is that you take some data, in this case it would be the email, and you attach some additional piece of data to it. It's called a nonce a lot of times. It's basically just like a number, any additional piece of data. And so you take your email nonce pair and you hash it and you see what the hash is, and you try to get the hash below some threshold. Like in the most extreme case, you would maybe be trying to find one exact hash, but that's for any realistic hash, that's way too much work. So more realistically, what you do is you try to get it below some threshold. And so let's say I type up my spam email and I attach the number 1 and I hash it, and that hash is too high. So I change the 1 to a 2 and I hash it, and that one's too high, and I keep going, blah, blah, blah. Eventually I find some nonce and the hash is low enough, and I send it over to your email server, and your email server says okay, I see he settled on the nonce 1337. Let me just rehash this thing real quick. Okay, it's good enough. I accept the email. And the thing is the good thing about it is that if I want to send 75 emails to all of you guys, I have to do that work 75 times. And so that slows down the rate at which I can send these spam emails. So that's the original context of proof of work. So Satoshi's big idea was to use proof of work as a permissionless leader election system in blockchain. And so his idea was okay, any node that wants to author, they do. They basically go ahead and author their blocks. They take the transactions out of the pool, build the whole block thing. And then they attach a nonce, and then they hash the block. And if the hash is low enough, great, that's a valid block. And if it's not, try the next nonce and hash it again and try again until you either find one that's valid, or more likely someone beats you to it and you get another valid block across the network. And so then when you get another valid block across the network, you just real quick verify it and then start trying to author again on top of that new block that you received. Oh yeah, go ahead, Aaron.
Would it be a potential then for somebody to spam what they say is actual valid blocks, which are not, in the hopes of all the other nodes spending all of their time then calculating whether or not it's a valid block, rather than trying to
just authoring bullshit blocks and sending them around just to distract everybody from trying to mine. Yeah, so that is a real thing, and there's a couple ways to address it. I think you're going to talk about peer reputation later, right? So I won't spoil that right now, but maybe even the phrase gives you some idea about that. Another observation is if I'm spending all my time spamming these BS blocks around, I'm probably not really spending much of my time actually mining valid blocks. So while I may be distracting all of my competition, I'm also not really making much progress myself. But this is a good idea. Yeah, I do want to say more. Okay, so let's just look at some pros and cons here. One pro that I'll list here is that proof of work is permissionless, or so we thought. If you read the Bitcoin white paper, for sure the way Satoshi portrays it there is that it's permissionless. It's the only requirement is that you have a computer with a CPU. Anybody's computer can compute hashes, and so we can all mine on this network. At least that was the original idea. But in reality, what happened is that it's now possible to buy super specialized hardware that makes you able to mine so fast that mining on my little dinky laptop here, or even my gaming rig or my moderately powered computer is a total waste of time and waste of energy. And you therefore have to be able to buy, afford this expensive fast mining equipment. So that didn't quite pan out the way Satoshi envisioned. So The next one, I'm going to list this as a pro here. Don't worry, it's also going to be on my cons list, so don't worry. One nice thing about proof of work is that it requires an external scarce resource, namely energy in this case. You have to power the mining rig, whether it's your computer or a powerful ASIC. And the thing that's nice about that is that it gives you a hint about how to evaluate the network. The more people are willing to pump this externally valuable resource into the network, the more they must be valuing it. Now, I'm definitely not saying that this makes network valuation like trivial or solves the problem, but it kind of gives you a hint. It gives you like one more concrete factor to use when you're trying to evaluate a network. So one thing that's like pretty much undebatedly, unequivocally good thing about proof of work is that it's blind. It has this property called blindness. And what that means is that nobody knows who's going to get to author next. You don't know who's going to find a valid block until the moment they find it and publish it. And the reason that blindness is good is that if you think of me as an attacker and you all as miners on this network, and I want to try to take out this network, I want to like DOS all of you, it's going to take me a lot of resources to DOS every single one of you. And proof of work, that's the best I can do, is to DOS every single one of you. Some other leader election mechanisms that we'll see shortly are not blind, which is to say I know exactly who's going to author next. And when I know exactly who's going to author next, I don't have to DOS all of you. I just DOS that one person. And when their turn ends, then I know who's going to author next, and I DOS that person. And it allows me to take down the network with much fewer resources. So blindness is a good thing, and POW has blindness. Okay, so another thing that's good about proof of work is that for the author, it costs something. It costs energy, and energy costs money in order to author competing forks. So if you want to kind of like mess up the network by intentionally creating forks, you have to pay to author both of those blocks. And at most, one of the blocks is going to make it in the final chain, and so it's a waste of money to do that. And in the same way that it's hard to spam email you with proof of work, it's hard to author all these competing forks to mess up the network. So these are the good things. Let's talk about the bad things. There are plenty of them. The biggest one that everybody's heard of is the energy intensiveness problem. So we live in a world of climate change. We live in a world of high energy demand and, maybe borderline energy crisis right now. And so there's an argument to be made that pouring all of this energy into blockchain isn't a good use of energy. I'm not going to take a position on that in front of everybody. I'll leave it up to you to think through it carefully based on what we're saying here. But I think it's pretty much agreeable to say that if we can preserve all of the good qualities of POW without the energy-intensive input, that would be great. That would be the ideal. And so many of the authoring engines that we see next are going to try to do that. Okay, so more cons of proof of work. One is an irregular block time. So we talked about quality block space. If you imagine you have an application that wants to get some transactions in, at whatever rate, or have some reasonable expectations of when it might be able to get transactions in, a regular block time is nice for that. It's good to know how frequently the blocks are going to be authored. Now, proof of work can achieve a probabilistically regular block time, which is to say, we know the distribution of the block times. We know that it's extremely unlikely to have a block right after another, and it's extremely unlikely to have a super long gap in between them. But we definitely don't know that we're going to have a block exactly once every minute or once every whatever it is. And so that makes it hard to work with in terms of treating it as infrastructure. And then the last one here is that it's not so permissionless for all the reasons that I already said. Well, on the face of it, hey, we almost all have computers, great, let's use them to mine, that's super permissionless. In reality, there's super high startup costs in terms of buying ASICs, and you also have to find a cheap energy supply. Okay. Some POW schemes, like Monero's, for example, strive to minimize the energy impact and maintain some permissionlessness by choosing algorithms that are ASIC resistant. So that means that it's impossible or extremely hard to make specialized hardware to mine them. And so that means more people will be able to mine on their everyday computers. So that does have real practical impacts in terms of reducing energy use and saving permissionlessness, but it doesn't fundamentally solve any of the problems. They're all still there. They just have some they've been engineered around to the best degree possible. Here I'll ask the question, why would one want to author at all? So if it costs energy to author blocks, why would anyone want to do it to begin with? Okay, so this is my third point. In many networks, there's explicit incentives for it. So in Bitcoin and most other networks, every time you author a block that makes it into the main chain, you get some block reward, you get paid some amount of Bitcoin. So explicit incentivization is a great one. Yeah.
For example, Monero. I mine Monero not to get the rewards, but to give the network more distribution.
Sure, yeah, if you value having a distributed network and that's something that you think is like a good use of your resource and make humanity better, that's a great reason. That's basically like altruism, as I'm saying here. And then another one that I'll just say is like to get your transactions in. Like we talked about how this block space resource is valuable and people want to get their transactions in there. And it may be the case that the value you get from getting your transactions attested to in this globally consensus shared story is worth the cost of mining or authoring the block. Nuke?
And also another network that's altruistic that I quite like to support is IPFS. There's no incentive there explicitly, but it makes me feel good, and I get to host my own data, so it's an intrinsic motivation, right?
Yeah, nice, nice. So I mean, to take it back to game theory, like the reason that you would author is because the utility that you get from authoring exceeds the cost. And these are some ways, some utility that people get out of authoring. So if you don't give a crap about altruism and you don't have any transactions, it might take the explicit incentives. Maybe for other people, it doesn't. Okay, so here we go. More authoring mechanisms. Proof of authority. So this is kind of like the traditional class of solutions. I mentioned that there was already distributed consensus before Bitcoin. So proof of authority is basically where there's some set of nodes who are predetermined and finite and are allowed to participate in consensus. And the typical way to do it is that you take the timeline from now until infinity and you divide it into these like fixed lengths. I guess they don't have to be fixed lengths, but they almost always are. Fixed lengths periods called slots. So you can say like slot 0 starts now and continues for 6 seconds, and then from t equals 6 up to t equals 12, that's slot 1, blah, blah, blah. And certain of the authorities are allowed to author in each slot, and you prove your identity with the signature. So instead of doing the proof of work, the hash preimage search, you basically just watch the clock and you say like, okay, it's slot 3, it's my turn, let me author a block, and then I sign it with my key. And then when I gossip it around the network, instead of making sure that my block hash is low enough, people instead check the signature and they say, okay, I was expecting Joshy to author in slot 3. Indeed, he's the one that signed this, so this block is valid according to the authorship throttling rules. So I want to say proof of authority is not a single authoring scheme. It's a whole family of authoring schemes. And so well, first I'll look at general pros and cons of it, and then we'll dive into a few specifics. So the big pro, it's low energy consumption. That's great. And it's also stable block time. So that is an ingredient for high quality block space. Okay, and then some cons. The obvious one, hopefully, is that it's permissioned. We don't have this valuation hint anymore since people aren't pouring in an external valuable resource like energy. It makes it harder to evaluate the network. And then with just plain, pure proof of authority, the incentives for honesty are not always clear. Like, what if all the authorities get together and decide to like misbehave or change the rules at the expense of the users of the system? And so what we're going to have to see is we're going to need some incentivization layer. Well, I mean, I guess I won't say we need it, but like if you want to restore some of these like properties about having your actors properly incentive aligned, we're going to have to add like incentivization layers on top. If you happen to have trust relationships with the authority for some other reason, like they're your family or friends, or they have a long history of acting honestly, that's totally fine, and some networks get away with that. But I think the less fragile ones and more unstoppable ones are the ones that have proper incentivization layers. So that's going to have to be a layer on top. Okay, so let's look at some POA schemes. There's many of them. So the simple one is Aura. It actually goes by many names. In the substrate ecosystem, it goes by Aura. It's basically like round robin. It's good because it's simple. And basically, you take all the authorities and you just go in order over and over and over again. And you can see the little snippet of code here. Like the authority who's able to author in this slot is basically like, look at the authorities list and just take the one whose index is this slot. And then like when the slot exceeds the authorities list, we're just going to mod it by the length of the list so it wraps around in order. So one pro here is that it's very simple. Another pro is that there's a single leader elected in each slot. So this is going to make forks a lot less likely. You know, we talked earlier, like the whole reason we're throttling authorship to begin with is because we're trying to reduce the number of forks to a manageable level. And Aura does a nearly perfect job here, but probably as good of a job as you can in terms of reducing forks. Now, they're still not impossible. You can imagine that like there's some valid block in slot 4, and then slot 5 comes, and I author the next one, but like my internet connection is crappy, and so the authority in slot 6 like didn't hear about my block in time, and they author another one that's a fork with mine. So Aura doesn't like eliminate forks entirely, but as long as there's like some reasonable assumptions on the network, it does basically eliminate forks. So the biggest weakness of Aura is that it's not blind at all. I know exactly who's going to author next, and therefore I know exactly who to attack to take the network down. So those are some of the trade-offs of Aura. Okay, the next one is BABE. It stands for Blind Assignment of Blockchain Extension. I just realized I forgot to put emojis on my slides. Next time. Okay, so the way that this works is that in each slot, each authority will compute a VRF output. So we learned about VRFs, I think, right? Okay, yeah, great. So I compute my VRF output, I get some number, and then if that number is below a certain threshold, that means I'm eligible to author. And so I go ahead and author a block, and the seal that I put on there is the VRF proof to show that this is what my valid VRF output would be, and then anybody can check that it's signed by me and that indeed my output is below the threshold, and therefore this block is valid. If not, if my output is not below the threshold, then I just do nothing. It's just not my turn in this slot. So the big advantage over Aura is that there's no longer a fixed order. We've restored blindness. No one knows who's able to author until the moment that they reveal their block. And so that means you can't DOS them in the moments when they're trying to author. And then there's some cons too. The big one is that some slots will have no authors at all. If it just turns out that none of the authorities have a VRF output that's like below the threshold, then no one's allowed to author here. And the opposite problem is also true. In some slots, multiple authors will be allowed to author, and then you'll have a fork in that slot. So like, let's say there's 2 authors eligible in this slot. We both author on the same parent. Now we have a fork. So I'll say there is like kind of an engineering solution here, which is actually what Polkadot does today, where you can combine BABE and Aura. So the main mechanism is BABE, but there's a fallback mechanism, and that is to say that in a slot where no one was elected by BABE, in a slot that would have otherwise been skipped because there's no author, there's also a round-robin candidate who can be like the backup there. So that solves like the first con, the one that some slots will be skipped. It doesn't solve the problem of in some slots there'll be multiple authors. And it's also not foolproof because you always know who the backup's going to be. The backup is Aura style, so like, you know, you can at least DOS the backup, even if you can't DOS we call it the primary, the one elected by BABE.
Sorry, I hope I'm not going to say something stupid, but I don't think the issue of not being able to know who is the next person to generate a block is about the IP address, but it's rather the fact that, imagine, for example, you could predict the next 10 people to generate a block. You could then bribe them to make a long line of blocks and then do a double span. So I don't think the issue is really in a denial of service and that you attack their IP, but rather, let's say you can figure out the next 10, you bribe all of them, and then you get 10 blocks, and then you double span. So I think that was the real concern, that it should be unpredictable. It's not for denial of service in the sense that you attack their IP, but rather to ensure you do not, make a kind of agreement with all of them to kind of fork the network in your advantage.
Yeah, bribe them. Great. Okay, that's a good point. So we haven't talked about double spends, but we will at the end of this lesson. So let me frame it as this: like, you're all authorities. I know the order in which you're going to author. I just go up to a few of you. You said like 10, for example, and I bribe you some money. And then what I'm bribing you to do is author a chain, but keep it private among us. And we'll reveal it later. And we're going to talk shortly about why it's valuable to like keep a private chain to reveal later. All right, so we talked about Aura, that's round robin. We talked about BABE, that's this VRF thing that is a little bit fork inducing, which is not always great. So let's talk about Sassafras now. This is a single blind VRF-based leader election, so that's a mouthful. It's VRF-based just like BABE. It's blind just like BABE, but it's a single leader election mechanism, just like Aura. So we're guaranteed that we only get one author in each slot, and that means we're going to get fewer forks, just like we had with Aura. So this tries to be the best of all the worlds. And this is a Sassafras tree, by the way. That's why there's like this tree on my slide. Other than I just love trees in general. So it has most of the pros of POW and all of the pros of POA. The only thing that POW has that is kind of missing here is like that external valuation hint. So, TBH, I don't really know how this works. It's really complicated, but I do know, wait, what's that? Yeah, this guy, Jeff, there he is. He works for the Web3 Foundation, and I had a little chat with him, and he explained how it works. It's kind of like Cards Against Humanity. So, who knows Cards Against Humanity? Yeah, all right, that's a pretty good amount of people. Just in case you don't know, I'll explain this card game. So there's 2 decks of cards. There's a black card and a white card. And in every round, somebody plays a black card, and it's something like this. I can't believe I got away with blank. Or, there's always a blank in there somewhere. And then all the other players play down a white card, and they play it face down, so you don't know who played which white card. But the white cards end up saying something like this: Best Rejected Paper Award. I can't believe I got away with Best Rejected Paper Award. Or, I can't believe I got away with the NSA's massive stack of amateur porn. And so at the end of each round, the leader, the person who played the black card, picks up all the white cards, reads them, everybody laughs, and then the leader selects which one's funniest, and whoever played that white card gets a point for that round. So Sassafras works kind of like this. Let's learn it in Jeff's words. Ring VRF outputs are cards. You anonymously play the best, aka smallest, card in your hand. Those cards are sorted, not by funniness, but by the number value. The order in which they wind up is the block production order. You claim the ones that are yours by doing a non-ring VRF with identical outputs. So did we talk about ring VRFs? Okay, well, we talked about VRFs, and did you talk about ring signatures? Okay, so hopefully your imagination can fill it in there, right? Like everybody has a VRF output, but because it's in a ring, you don't know which output corresponds to which person, just like how you don't know which signature corresponded to each person. So in Cards Against Humanity, it's like kind of an honor system when you say like, oh yeah, that was my white card that I played. But here we're talking about like blockchain, so we have to prove it cryptographically. So when you want to say like, oh yeah, that was my ring VRF output, the way you do it is by revealing the same VRF without the ring. He also said in our chat like, or some other ways. I don't know what that means, but this is Sassafras. So just to recap, it's very similar to Babe in that it's VRF-based and that it's blind, but it has the advantage of Aura in that it elects exactly one authority to author in each slot, and so that reduces the number of forks even further, which was the whole point of throttling authoring to begin with. Okay, so now let's talk about proof of stake. Here's the big head explosion. Proof of stake is actually just proof of authority in disguise. So all of these same methods, Babe, Aura, Sassafras, that I just talked about for proof of authority, these can all be made to be proof of stake methods. We just use an economic staking game to select the authorities. So instead of like deciding who the authorities are once and for all, we're actually going to use our state machine to execute logic where people can stake tokens and then become the authorities. So it restores the permission list to like roughly POW levels. And what I mean by that is you no longer have to be selected as one of these privileged authorities. You just have to put some tokens in. Now, the obvious criticism here is like not everybody has tokens. How are poor people ever going to get to participate? That is a valid criticism. That's something that I hope we all strive to like improve. But I do want to make the point that this criticism also applies to proof of work, because how are poor people ever going to afford ASICs or the electricity to run them? So I'm optimistic that in the end, proof of stake can be more permissionless than proof of work, but as we now know, neither one of them are truly 100% permissionless where anyone can come up with nothing but the clothes on their back and join in, and that's something that we can strive to improve. So the other thing about proof of stake that's really nice is that it restores clear economic incentives to the protocol. So there's a million proof of stake games. There's a whole rich design space for economic games that work for proof of stake, and Kian's going to talk in depth about one that's used in Polkadot at some point. But the way it generally works is that like anyone can lock up tokens on chain. So by on chain, I mean like in the state machine. There's a state machine transition that's called like stake, and you lock up some tokens. And the participants with the most tokens and staked are elected as the authorities. And there's also a state transition that allows reporting authorities who misbehave. So think about authorities that author when it's not their turn, or authorities who fail to author when it is their turn, or authorities who author when it's their turn, but also author another block at the same height when they weren't supposed to. All of these things are things that are bad for the network, and they're all things that are reportable within the stake machine. And when you get ratted out for doing one of these things, the stake that you put in gets slashed, which is to say you get some or all of it taken away. And typically, the reporter is like given a reward for doing this, so there's some additional explicit incentive for like narking out the misbehaving validators. There's also, I'll say this, like, so when I stake my tokens, there's some opportunity cost. By having them locked up in staking, I can't use them for buying real world goods or any number of other things that I might want to use them for. And so for that reason, there's typically still like an explicit block reward, just like there was in proof of work. And I didn't say it at the time when we talked about proof of work, but the block reward, the fact that you get tokens for authoring blocks, that actually happens in the state machine, because the state machine is where the tokens live. So let's see here. Yeah, so that brings me to this side. Consensus and state machine. It's a love story. So far, I've talked about consensus and state machine as totally orthogonal concepts. Like the state machine is the thing that we're tracking the history of, and the consensus is the thing that we're using to track the history. And that's a really good approximation. That's like really close to true. In some cases, it's even literally true. You could imagine like a proof of work chain that doesn't have a block reward, and then there it is, it's literally true. Or like a simple proof of authority chain where you just trust the authorities to author because they're altruistic, and it's literally true. In reality, there's typically a loose coupling between the state machine and the consensus layer. And so, for example, block rewards, if I author a block, I insert into that block a transaction that says, yo, I, Joshy, am the block author, and the side effect of that transaction is that I get some tokens. And then like we already talked about, there's the slashing. If someone reports me for misbehavior, I get slashed in the state machine. So I got caught misbehaving in the consensus layer. Someone reported that provably to the state machine, and I got slashed in the state machine. And then there's like the authority election itself. You know, people stake their tokens in the state machine. That's where you run some algorithm that decides like who has the most tokens. And then they're the authorities in the next round. And like I said, the authority handoff typically happens at like an epoch boundary. And so then like even in POW, well, first of all, there's the block reward. But in POW, there's also this thing called the difficulty adjustment algorithm. So you can imagine if we just set our proof of work difficulty threshold to like some value, whatever it is, and we're like all mining, and like, you know, we get a block like probabilistically, let's just say every 1 minute. And then all of a sudden our chain gets popular and a whole bunch more people come in and start mining. That's going to make our block time speed up. And if we want to keep a regular block time, that's bad. So what you do is you tune the threshold to like react to the mining power that's on the network. And so that's another example of like coupling between the state machine, where this algorithm runs, and the consensus layer, where we use the threshold to actually decide who's eligible to author. Ah, yeah, great. I knew I was forgetting something. I'm glad I wrote it. So this is not the Substrate module, but just to foreshadow a little bit, in Substrate, there's this concept of a runtime API. Keon's going to talk all about them. You're going to implement them. You're going to be experts on runtime APIs. This is the tool that you use to implement the marriage between the consensus layer and the state machine. So it basically allows off-chain processes, for example, the consensus layer, to read information from the state machine. And so like what kind of information might we want to read from there? Well, the difficulty in POW, or the authority set in proof of stake. So, okay, right. All right. Zoom way out. Remember at the beginning of my lesson, there were like 5 main concepts. There was state machine validity, there was the political validity, there was the authorship throttling. This takes us to the 4th one, which is fork choice heuristic, and then the last one's going to be put off till tomorrow. That's finality. So here's how fork choice heuristic works. Each fork choice heuristic, or fork choice rule as it's often known, is like basically each node's preference for which fork is best. So each node runs this thing on their own, and it says, based on the blocks that I've seen, here's the block that I think is the best one so far, or like the tip of the best chain so far. So the classic one that everybody's probably heard of is the longest chain rule. It was originally introduced in Bitcoin. And so like if this is the blockchain data structure, as far as I've seen it, this would be my best block because it's the longest chain. There's other ones, and you're going to implement several of them in blockchain from scratch. But another one would be most accumulated work. So this depends on proof of work consensus. And the idea is basically that like maybe this chain is longer, but maybe this chain has a lot more proof of work behind it. And so we'll actually consider it better. Another one that works with proof of authority or proof of stake, since it's actually proof of authority in disguise, is which chain has the most blocks that were authored by a particular person. Now that's like a little bit of a weird one and like leads to centralization. I'm just giving you like the example of the kind of thing you can do. That's not like a super realistic one. Or like, you know, if you think of something like Ethereum, I know we haven't dove super deep on Ethereum, but they have this notion of gas, where gas basically represents like how much compute has happened in the state machine. You might choose the chain that has the most total gas consumed, or basically a way to think of that is the one where the state machine has done the most total work. That allows you to like optimize the amount of block space that's being consumed in your chain. Anyway, there's a whole bunch of these. When we look at diagrams on the screen, we're basically going to use longest chain rule because it's just easiest to point at and everything. So like, okay, here's my longest chain. This is my best block. That means if I get to author next, I'm going to author here. I'm always going to extend the best chain. But the thing to realize is that not everyone has the same view of the network. It might be that other people in the network haven't actually heard about these two blocks yet because they just like didn't make it across the network yet. And so some people, two different honest parties who are following the same fork choice heuristic can have different understandings of what block is best just because they have different views of the network. So that leads me to reorganizations, aka reorgs. So, all right, imagine that you have this view of the network. It's the same diagram I showed before. This is your longest chain, so this is your best block. And then all of a sudden, your ISP starts giving you a lot more bandwidth, and you download all this data you were waiting on. And now you have this view of the network. So we've still got all of the same blocks we had before, but we now have two newer ones. And so this is now our longest chain. And what that, assuming we don't have finality, because we haven't talked about finality yet, what this means is that you're going to do a reorganization. You're going to change your mind and say, okay, well, I used to think this was the best block, but now I see an even better one, and so now this is the best block. And reorganizations can be a bit of a pain. This is one reason why we try to minimize forks. The other reason is what I already said, which is that it makes consensus just take longer to reach. And the reason that it's a pain is because you might have had a state transition in this block that you really cared about, and now no one considers this the real chain anymore. This is the new real chain. Now, typically what happens is that like if you had a state transition in here, it's probably somewhere in here too. But if it's not, what nodes do is that when they abandon a chain like this, when they change their mind away from it, they take all the transitions that they had in there and they throw them back in their transaction pool so that they can quickly add them into the next blocks as the chain continues to grow. So reorgs are basically changing your mind about the state of the world. So you can actually like experience this in a social way too. It's not like strictly a blockchain phenomenon. So like imagine you're waiting for a colleague to submit a paper and you believe they submitted it yesterday, but it turns out that they didn't submit it until today, or like maybe they won't submit it until tomorrow or something. That's like an example of a reorg where you change your understanding of the state of the world. And in the example I just gave, like it's probably annoying, but maybe not earth-shattering because like, all right, whatever, it's gonna get in tomorrow. I'm just like annoyed at this person now. But you can also experience it like on larger levels. Like imagine that you believe a colleague submitted the paper months ago and the paper was published, and you've like applied for a job having listed this publication that you believe is coming up in the next issue, and then it turns out the person just like didn't publish that paper. You're probably going to be really mad. It's really affected the state of the world. It's affected your chances to get this job. It's made you look like a liar in front of this person who you submitted the application to. This is an example of like a bigger, more impactful reorg, and so in the analogy, it basically means like more blocks were abandoned. We reorged into like instead of this fork being like 2 blocks deep, maybe this fork was like way back here somewhere, and we really have to change our understanding of the state of the world. All right, so here's how a double spend attack works. This is the same chain that we had before, and if you remember, like originally we saw these blocks in the ancestors, and here's a transaction where I've like paid a counterparty. So let's just say it's like Andrew, and he's gonna like sell me his motorcycle, so I like send him the money. We see that it's in the blockchain, so he gives me the keys and I like ride off on his motorcycle. And then what happens is that a longer chain comes out here, and everybody on the network reorgs away from this history that has the transaction where I paid Andrew for his motorcycle. So under normal scenario, this sucks because he doesn't have the money anymore, but it's not the end of the world because he's hoping that this transaction like either is already in one of these blocks or else it's going to be in a block soon on the like newly understood to be real side of the fork. The way the double spend attack works is that I already have a conflicting transaction in the new side of the fork. So I took these same coins that I paid Andrew, and I paid him to like my friend who's in on it. And like in reality, the friend might also be me, like my other account or something like that. And so what happens now is that because these two transactions conflict, it's impossible to ever put this one into the new fork. It's already like ruled out by this one, and this is how you get away with the double spend attack.
The one thing I want to point out is that I think some people I've talked about double spend, they think that submitting two transactions which conflict is double spend attack. But I just want to clarify it's not. Like the double spend attack is like perfectly valid for me to have like 5 dot and send 5 dot to Joshy, 5 dot to Dan at the same time, like in the transaction pool, all that kind of stuff. That's perfectly valid. I'm not an attacker at that point. The attack is when you try to build a secret chain, keep a secret transaction, and then reveal it last minute to switch things out. Like that whole process is needed for attack. And I guess one more thing I would like to think about is like, if anyone's used Ethereum, one of the cool things you can do is like, if you have a transaction that's taking too slow, you can like cancel the transaction, or you can speed it up by like submitting another transaction with the same nonce and like change the parameters, right? In many ways, that is basically the same thing. Like I'm submitting the same transaction or transaction nonce twice, but again, it's not an attack. This is a feature. The attack is specifically like doing all of these things. So when you think about double spend attack, don't think about a user just submitting two transactions which conflict. It's this whole process of kind of collusion.
Yeah, you got to get them. You got to get one publicly known first. You got to get the other one on the other chain, and keep the other chain hidden until you've already gotten the keys to the motorcycle. It can be quite challenging.
And I guess one last thing is like, I think when we talk about the word security, it's in a lot of ways it can kind of point towards like how much resources does it take to do something like this.
We talked about the first 4 in this lesson, and we're going to talk about finality tomorrow morning. So, all right, that's where I'll end it. Thank you guys so much for your attention today and your hard work on the coding.